Welcome back. Now I have the pleasure to introduce Liam. Liam, welcome.
Hi, everybody. My name is Liam Taylor. Hi, everybody. My name is Liam Taylor. I'm with EXA Infrastructure. I'm here to give you an update just on things that have been happening with submarine cables and the submarine cable industry. So first, a little bit about EXA. We're the owner-operator of 3 cables in the Atlantic. We also have a presence on several other submarine systems, and we've also got numerous unrepeated systems connected to other parts of Europe. So how we're going to go through this is we're going to talk initially about what's been happening on a transponder level, then we're going to move it up to what's happening on a fibre pair level, onto a cable level, and then some of the advancements that are coming down the line, but maybe aren't quite here just yet. Then we're going to talk about some general updates on some other topics that have been happening in the submarine industry, which might be of interest to you, particularly as a lot of you would operate on a higher level on the IP level. So just a quick little bit of background first on the nature of a submarine cable. In the center of the cable, we have our fibre pairs. Obviously, that's where our traffic is being carried. Then we'll have some insulation. We'll have a layer of iron just for protection, of steel for protection. We'll have a copper carrier to power our repeaters. Then we'll have layers of insulation and additional armoring if it's required in shallow water. We'll have our cable stations on either end where our fibre will connect. They'll be providing power and the optical signal for the cable. Each of the cable stations will be able to power the cable fully. Just if we need to take the cable, if we need to take the PFE on either end offline, we'll be able to power the entire cable from one end. And if we do have a shunt fault, an electrical fault somewhere on the line, we'll be able to keep powering the entire cable, even though the power mightn't be able to reach where we expect from the other end. We'll have repeaters depending on the generation of the cable, every 45 kilometers up to maybe 100 kilometers in some of the newer cables, and that will make sure we'll have optical continuity throughout the cable. So on the transponder level, initially, if we're talking the early 2000s, we'd have quite simple transponders, which would use very simple modulation, like on-off keying or non-return to zero, using either amplitude or phase to send a single symbol carrying a single symbol carrying a single bit. But as things progressed, we were able to move on towards using more advanced modulation schemes, which would use amplitude and phase. And we're able to use QPSK, 8 QAM, 16 QAM, all the way up. And that enabled us to increase the data that we're sending down a wavelength, because each symbol that we're sending is then sending multiple bits of information for every pulse. Now, that's not without issue. As you get up towards your higher constellations, when you look towards the edge of your constellation, those bits are a lot more prone to error. So what most vendors have switched towards using now is that they will use probabilistic constellation shaping, where the most common symbols will be sent towards the center of your constellation. And that will make sure that the most common data and the most common symbols are sent without error, or with less error. So when you're using your digital signal processing and your forward error correction to remove any errors, that you'll have a much better signal and much better continuity through. Taking a look then on a fibre pair level, if you look at our legacy systems, so we're sticking to the systems that went in the late 90s, early 2000s, we had very little of our C-band that was actually usable. You're talking about maybe 2 terahertz, 2.2 terahertz. As we progressed, when we were able to move up, you'd be able to have the entire C-band, not the extended C-band quite yet. These days we can get the extended C-band, but then we were talking about just a little bit of the C-band in of itself. And we were looking at 100 gigahertz signals. As things progressed, we were able to reduce that down to 50 gigahertz, and now what we've moved towards is actually using fixed grid. So if we look at using flex grid, if we look at the fixed grid system over there, you can see all of the 50 gigahertz signals being muxed into one line. Those signals, the 50 gigahertz signals, aren't actually 50 gigahertz signals. What they actually are is 37.5 gigahertz signals with 12.5 gigahertz spacing in between them, just to make sure that the signals don't interfere with each other. So one of the big advantages, and one of the things that's massively increased the amount of data we can send down a cable, is the move to flexible grid, because rather than having those 12.5 gigahertz of just dead space insulating our signals, we're able to bring our spacing right down. If we look at modern transponders, you're talking about a gap of maybe as low as 3 gigahertz between your spaces, between your signals. We've also increased the size, the width of our signals. If you look at a modern transponder, you're talking 140 gigahertz, 200 gigahertz compared to that 37.5. And what this is doing is just massively increasing the spectral efficiency and really cutting out on any dead space that's in our spectrum. So you can see over time, we were talking in the early 2000s, even with, we were talking about 48 10 gigahertz, 48 10 gigabit signals, only 480 gigs on a transatlantic fibre pair. Moving all the way up to a modern system, we're talking about 36 signals doing 800 gigabits. Massive increases over time. There is a limit to the amount you can transmit on a fibre pair, and that's defined by Claude Shannon, by a thing we call the Shannon Limit. As you can see from the terminology there, there's a close ratio between your signal and noise. The noisier your system, the less capacity you're going to be able to get through. And if you have a nice clean system with very little noise and high signal, then the amount of capacity you're going to be able to get through really increases. There is a slight problem with this though. We can never quite get to the Shannon limit. There's always a bit of a gap. And the main reason for that really is that fibre is not a perfect material. Fibre is a non-linear material. As we increase the amount of power going in, optical power going into our fibre, there's a certain point where the non-linearities really start to cause impairments. Up to a point then where if we go past that level, if we throw additional optical power into our system, it actually begins to actively impair our signals. As well as an optical limit, there's an electrical limit to the amount that we can put into our cable. If you look there at the structure of our cable again, we can see our copper carrier. It's quite thin. If we try and put more current down that, we'll short it out. We'll end up with a shunt fault in our cable. We'll have to go out and repair it. We could try and use a thicker carrier, but if we do that, there's only so much room inside our cable. We'll discuss that more a little bit later. If we start increasing the thickness of that copper, we're going to need to make sacrifices elsewhere. We could try and use different materials. That's going to have massive cost implications. The more and more we do to try and get closer to the Shannon limit using the existing techniques, the less return we're getting. On a terrestrial level, when you start to run out of capacity, there's a very easy solution. If your C-band is maxed out, we can start to look at the L-band. There is a problem with doing that on Submarine, though, in that a C-band amplifier will not work for the L-band. It's a totally different amplifier. So what you need to do is you need to deploy an entire second set of amplifiers, and you're going to need to put splitters in front of and behind your amplifier in order to separate the signals out. That will add extra losses to your system. So not only are you doubling your power requirement by doubling the amount of amplifiers you're using, you're also introducing additional losses which will impair your existing C-band spectrum. L-band amplifiers are also less electrically efficient than C-band amplifiers, so you're going to be more than doubling your power requirement. So for us in the industry, we've looked at it and decided that it's more efficient, more cost efficient for us to add more fibre pairs rather than trying to get more out of individual fibres. So we may come back to using CNL when we exhaust the techniques we're looking at now, but for now, our preferred solution is SDM. So what is SDM? SDM is spatial division multiplexing. Before, we looked at wider repeaters, more expensive fibres, more expensive transponders, and continually getting as close to the Shannon limit as we could. But our current our current approach with SDM is to look at using standard fibre, standard electrical carriers, or even using cheaper carriers like aluminium, and focusing on the efficiency of the repeaters that we're using. And what that means is we can make our fibre pairs as cheap as possible and reduce the overall cost. If we take a look at the graph on the right there, if anybody remembers your base 10 logarithms, your rule of 3 and 10, if we take a look at one fibre pair on the lower line, if we increase our output power by 3 dB, we only get about a 4 terabit increase on the amount of traffic that we're getting on one fibre pair. If instead we take that 3 dB increase and we stick a splitter there, and we separate that power out onto 2 fibres, we can then power 2 fibre pairs, which gives us 40 terabits of capacity. So although we're getting less out of a fibre pair than potentially we could, we get much more out of our system overall. And that's really what's at the heart of SDM. Taking a look at some examples of systems that are commissioned. So we have EXA North and South, some older cables was rent in 2001. We've done some upgrades over the years, but the capacity of those cables is still only about 5.4 terabits. We're getting the next generation of hardware in now in the next month, and we're hoping that the trials there will give us a bit more uptick. We'll get a bit more life out of those cables, but we'll have to see how it goes. Looking at Maria, which was laid in 2018, you're talking about 26.2 terabits per fibre pair for a total capacity of 209 terabits. Moving on then to a cable using SDM, we have reduced the amount of capacity that's on a single fibre pair down to 25 terabits, but overall the cable capacity has increased to 300 terabits. So what's the next step then? Our cable only has so much side. In general, the standard cable that's used in the industry is SL17. That's your standard deep water cable. There's only so much room inside of it, and there's only some parts of it cannot be sacrificed. We can't use smaller wire, the protective steel mesh. That will make our cable much more prone to damage. We can't go for a smaller conductor because we'll increase the amount of shunt faults that we're going to have on our system. We can't go for a smaller, smaller insulation. We can't go for a smaller conductor because that would mean we'd have less power down our cable altogether. We can go for a thicker gauge of cable, SL21, but there's a big cost implications of that because in general the industry is set up to produce as much SL17 as possible. So we might be talking about having to retrofit factories, we might be talking about having to retrofit fleets of repair ships and lay ships in order to deal with more SL21. And believe it or not, there could actually be massive cost implications for laying the cable itself. It might not seem like much difference between a 17mm cable and a 21mm cable, but if you have a hold of a ship and you have 6,000 kilometers of SL17 in there, and you increase the dimension of your fibre of your cable by 2 millimeters in every direction, you might be talking about only getting 4,000 kilometers of cable in instead. So you're going to have to do 2 runs across the Atlantic instead of one run across the Atlantic to lay your cable. So what can be sacrificed? Well, our cable is being molded into another cable. So maybe it doesn't need, each fibre pair does not need as much protection as a standard fibre might. So what's happened is that the coating that's around our cable, our core and our cladding remain the same, but the coating that's around our cable will be reduced from 250 micrometers to 200 micrometers. Now what that means is that we're able to increase the fibre count from a maximum of 16 fibre pairs up to 24 fibre pairs. Currently there's a bit of a higher cost from doing that, but as scale comes online, that cost may reduce. Take a look at our chart again then. If we look at Anhana, which was laid just 4 years after DENOG, it's increased to 24 fibre pairs. Each fibre pair is only getting 21 terabits, but the cable capacity itself is all the way up to 504 terabits. Absolutely huge increase in capacity. So that's where we are today. Where we're going now is, and there is a cable that's being laid with 2-core fibre in it. There's the Taiwan, Philippines, US cable that's being laid by Google on one of the branches from the Philippines to Taiwan. They are laying it with 2-core fibres. So we're looking there is we can't fit any more fibre pairs in, but maybe we can stick an extra core inside of our cladding. There is some reduction. There is slightly higher attenuation. There is a slight bit of crosstalk between the fibre pairs and the 2-core system, but we're doubling our capacity. We're doubling the amount of pairs that are available to transmit on. So there's potentially massive increases in capacity here. Now, there is some additional problems, particularly when we start to move up to 4 cores. There's a lot more crosstalk on a 4-core system. If you're looking at a one core pair, you will have you'll have one signal transmitting in one direction and one signal transmitting in the other direction. So just like with your old twisted pair in copper, you can reduce the crosstalk by not having things transmitting in the same direction. When you start to use 4-core, well, you're always going to have 2 things transmitting in the same direction at any one time. So there is going to be a crosstalk issue. But again, if you look at it and say, okay, well, I got a 20% impairment per pair, maybe my 20 terabits per pair will go down to 18 terabits per pair. But if I get to double or quadruple the amount of cores that I'm dealing with, absolutely huge increase in capacity. FIFO is fan in, fan out. I probably should have spread that out for people. It's basically just how you split the cores onto some kind of medium, so you can then amplify it or break it out onto something else. So that's largely where the industry's been going. I guess some general updates for you guys on other things that are happening that may be of interest to you. So one of the big things that have been happening in the last couple of years is spectrum sharing. So for spectrum sharing, there can be a part of a network, your network's growing, you're leasing individual 100 gigs, you're leasing individual 400 gigs, and maybe the demand that you have outstrips those 100 gigs and those 400 gigs. But you don't quite have the budget, or maybe you can't get access to a full fibre pair. They are limited. There's only so many fibre pairs going across the Atlantic. You need a lot of expertise to operate them. They can be quite restricted. But maybe you might want to take a half a pair or a quarter of a pair, and this is where spectrum sharing comes in. There's a little bit of an issue. In general, there have been multiple vendors doing it. There have been multiple customers, multiple equipment manufacturers, and everybody's been using their own terminology. But thankfully, Suboptic, which is one of the big bodies working in Submarine at the moment, has come along and issued a white paper. You can access the white paper on the Suboptic website. And what they've done is they've gotten a bunch of vendors together, gotten a bunch of the cable operators together, and come up with standardized wording and standardized arrangements for the different levels that are in operation. So it's quite clear. If you are interested in spectrum sharing, you can have a chat with me later on, or if you want to go to the Suboptic website and check out, where would you fit in? Would you be a level 2 user, a level 3 user, a cable operator, cable owner? It's much clearer, and everybody has standard terminology to work with. Another thing that's been happening quite a lot, historically, SLTEs and submarine cables, they were very locked down. You'd go to a manufacturer, they would give you a turnkey solution, they'd expect you to use their SLTE, their submarine line terminating equipment, their GUIs, and they'd have no northbound or southbound interfaces for you to interact with the equipment. In general, the industry's been pushing more and more towards using any SLTE, having standardized naming conventions, and then having a clear interface that we can use and log onto to get clear input and outputs. So that's been more and more adopted. The Open Cable Management Working Group, again, has issued a paper. This is the second edition that they've done, and their work is ongoing. And basically what they've done is, apologies, the text may be a little small here, but now everything can be operated with simple get and set commands. The format is very machine readable. You get a nice little output there. And it's a massive improvement, to be honest, because, like I say, it used to be everything was locked down, and you used to have if you wanted to have any kind of thing that wasn't from the vendor, it was a complete pain. Coherent pluggables, you may be familiar with. I know a lot of people are using them on a terrestrial level. They're not being used much on a submarine level. Basically, a coherent pluggable allows you to, rather than the traditional setup where you'd connect your router or your server directly up to a transponder, which would then translate that into a C-band signal to connect up to a MUX architecture. What we have with coherent pluggables is that you can stick a C-band optic directly into your router and to access the MUX architecture directly. There's a lot of benefit for that. You can get rid of your interim devices in the middle. You can have modern spectral plans and really get the most out of your fibre. But it's not really being seen on a submarine level. And really that's down to your little pluggable in your tiny form factor, your QSFP DD, just can't compete with the amount of processing power that's on a full transponder. A modern submarine transponder will have a lot of different optimization modes to get the most out of the forward error correction in the board to really get the distances you need. And they'll also have a massive amount of dispersion. So you may be familiar with chromatic dispersion. As you go through any medium, your signal starts to broaden. A modern submarine cable will have 120,000 picoseconds worth of dispersion, which there's no way a pluggable is going to be able to do that. Finally, the last topic that's huge in the industry right now is sensing. So sensing is basically using submarine cables as a sensor. A lot of different applications being worked on, from early warnings for tsunami, detecting earthquakes, monitoring environmental conditions in the ocean, and then from a cable owner operator's perspective, how can we protect our cable? So if we can deploy sensing on our cable and we can detect when fishing activity, because fishing activity is the #1 cause of fibre outages. If we can detect when fishing activity is happening near our cable, we might be able to prevent damage, increase reliability, and reduce costs for us in terms of repairs. And then there's also a lot of talk at the moment about security. For me, it's about fishing. If anyone were to be tampering with your cable deliberately, monitoring systems from sensing should be able to help you out. There's a lot of different approaches. I'm not going to go too much into that because there's a lot of There's a lot of different approaches. Each have their benefits and drawbacks. DAS requires a separate unit. Interferometry and SOP can use transponders that are on your cable, so there's not much extra investment in it. And smart cables require totally separate units to be installed in your cable. So that's really done at build. A lot of different advantages and drawbacks to them. If you are interested in it, there is a working group in Suboptic, and they do publish papers periodically. It's a very hot topic for research at the moment. So does anyone have any questions?
I see one back here.
Yeah, hi, I'm Will from CITES. I was wondering if how much you have of a flexibility in those cables. I mean, you mentioned the tsunami and so on. Do the length oscillate a bit on such a distance and like then the latency between 2 points? Because obviously I suspect that those things are not like exactly fixed. They are, you might have a bit of flexibility in the length, and so I'm wondering if that affects the potential distance between 2 points, like through the Atlantic, for instance.
The latency will be fixed because certainly in more tidally active areas and on the continental shelf, you'll bury your cable. You'll try to bury it to a depth of 2 meters, which would restrict any amount of movement back and forth. I mean, some movement will happen, and you know, you lay your cable and 20 years later, it might not be buried anymore. Or we went to do a repair before, we buried our cable at 2 meters and it was 8 meters down because so much silt had accumulated. But in general, your cable isn't going anywhere once it's down. Like a cable, even though it's 17 millimeters, it's quite strong. Like you're not going to be able to bend it.
John Howard from Proton. I have a question that seems to be coming up over and over again when it comes to submarine cables. That it seems to be very much a private industry in terms of the awareness of when there's problems. If you don't have a Kentic or access to Thousand Eyes or something similar, it's impossible to know whether there's an actual problem somewhere out in the community. There's a failure of that cable or a failure of another. Is there anything going on inside that submarine cable community to expose these errors and outages to the general public?
Generally, no, because outages would be considered commercially sensitive. You know, if I have an outage on my system, be it a full break, I mean, a full break people are going to know, but if it's a shunt fault, you might consider that to be commercially sensitive information, so you might not want people to know. As is, in the industry, we tend to know, but that information might not be widely known. Because what we'll often do is, if I have a fault, let's say I have a fault in the English Channel, and you have a fault somewhere in the North Sea, well, if I'm getting a repair ship out to fix my cable, I might try and reduce costs by having the ship pick up my spares when they're on their way to do your repair. So then they'll hit your repair, do your repair, and then do mine on the way back. And then we don't have to pay for as much transit time. So in the industry, we tend to be aware of what faults are where. Information at large, not that I'm aware of. I don't know that anybody's working on that now.
I could actually add the DENOG group list. It's very interesting for this because they track all the cable outages. And then you see, no, they do it because they depend on cables and submarine cables. So you hear about them on DENOG. So.
David Lamperter, forwarding. With all the various approaches to cram even more data through the fibers, does that affect the aging and like deterioration of the submarine cables, or is that independent of?
It's actually helpful to have your cables powered. You don't want to leave your cables inactive. One of the biggest differences between transmitting on a terrestrial level and a submarine level is day one on your submarine pair, you're going to transmit your entire spectrum. And it's just that the amplifiers have been optimized to deal with that. If you don't have any current going through if you don't have any optical power going through your fiber, you might end up with problems with your repeaters.
I meant in the long run, like if after 10 years or something, is the cable slowly going to degrade in terms of maximum capacity? Because you're now putting like multiple cores in one cladding and doing even fancier modulations that are more noise.
I mean, a photon's a photon, you know. It doesn't really matter what kind of, like, if you look at our older cables, like the EXA North and South, when they were initially turned up, they had 160 gigabits on them. We're now talking about 5.4 terabits, and we're hoping maybe with the next generation of transponders we'll get 8 terabits. Cables are designed to have a 25-year shelf life. They might run for 50, you know. Like all the cables that went in the late 90s and early 2000s, people are making decisions now based on just the finance of it. You know, is the cost of maintaining this cable worth the amount of capacity I can get out of it and the revenue that I can generate from that? At a certain point, those numbers won't add up, and people will start turning those cables off and recovering those assets. But for the moment, no, we'll just keep upgrading things.
Okay, we've run out of time for questions, so thank you very much.
Thank you.